Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Previously in this unit, we've talked about dilations, and then we talked about proving polygons similar to one another. Well, in this lesson, we're going to focus strictly on circles, and then moving forward, we will focus specifically on triangles. But circles are kind of a separate entity because they don't fall into the polygon set of figures. We will do the do now, because this is going to be a short lesson anyway. So work through these first four problems, pause the video, and then come back and see how you did. Okay, so number one says find the image point given the stated transformation and the pre-image point. So we have a point 2, 4, and this is going to be a translation. We are adding 3 to each x-coordinate and subtracting 1 from each y-coordinate. So our image point is going to be 5, 3. For number 2, we have our pre-image point of -2, 1. Our x-coordinate is staying the same, so that's going to be -2. And our y-coordinate is changing sign, so it's going to be -2, 1. This would actually be a reflection over the over the x-axis. So you could sketch these 2 points if you wanted to. Again, we would just be reflecting over the x-axis. For number 3, we are given a pre-image point of -5, 0, and we are multiplying both the x and the y coordinates by 3. So we get -15, 0. This would be a dilation because we are multiplying each coordinate by the scale factor, which in this case would be 3. Finally, for number 4, we are switching the coordinates, and the y-coordinate is becoming negative. So we end up getting -6, 2 here. And again, this might be hard to think about if you are just trying to do it in your head. But if we think about what's going on a coordinate plane here, we start off with 2, 6, which is somewhere up here. Then we have -6, 2. This would be a rotation 90 degrees counterclockwise. Or if you wanted to go clockwise, 270 degrees clockwise. I remember rotations are where we switch the x and the y coordinates for each 90-degree rotation, and we choose the correct sign. Okay, let's start talking about circles. Before we do that, though, let's review from last lesson. How can we prove that 2 polygons are similar? So think about the definition or the criteria for 2 polygons to be similar. And for this first question, I'd like you to focus on not necessarily what has to be true about the sides and angles. We'll get to that in question 2. But think about maybe in terms of transformations. How could we prove that 2 polygons are similar? Well, in the answer to that, just like congruent figures, we have to map them together using a series of rigid motions. To prove that 2 polygons are similar, we need to be able to map one onto the other using a series of transformations. And the 4 that we would use could be translations, reflections, rotations, and dilations. So with similar figures, we may have to make a figure smaller or larger, which would require a dilation. Now, if we think about what's going to be true about the sides and angles, well, corresponding angles in similar figures will be congruent. Remember, the angles don't change. Corresponding, if I could spell corresponding, corresponding sides will be in proportion to one another. And what this really means, right, i.e. they have the same scale factor. So angles, they have to be the same, they have to stay congruent. The sides can change as long as they have the same scale factor. Well, let's dive into circles a little bit. So are circles polygons? Why or why not? So I just kind of mentioned that they weren't a couple minutes ago, but think about why they're not. Think about the definition of polygons and why circles do not fit into that category. Okay, so if we think about the definition of a polygon, right? A polygon is a closed figure made up of segments. So problem with circles is that they're made up of curves, right, rather than segments. So no circles are not polygons because they are made up of a curve rather than segments. Nonetheless, we still can prove that circles are similar. So I'm actually going to show you guys a little demo. We're going to hop over to GeoGebra. So give me a second to pull that up, and then we will continue our discussion. Okay, so we are over here at GeoGebra, and our goal is to prove that any set of two circles are similar. So let's think back to what we need to do that. Right? We just said that to prove that two polygons are similar, we would have to map them onto each other using a series of both rigid motions and dilations. Well, we're going to see if we can do the same thing with circles. So I am going to try to map the blue circle. I believe we're going to be moving the blue. Nope, we're moving the green. So we're going to be trying to map the green onto the blue. Well, think about what we need to do, what we would need to do that. What rigid motions would we need to use, and would we need to use a dilation or not? Just think about, which rigid motions, which rigid motions we need to use, and what kind of a dilation would we need to use. Well, we could first start off by doing a translation. So I can move the green circle to the left. I can move it down until B was mapped onto A. And then I would need to use a dilation because I need to blow or enlarge the green circle up. So my scale factor would need to be greater than 1. And I would just make it until they were the exact same size, like that. So I have mapped the green circle onto the blue using a translation and a dilation, which means that these circles are similar. Now I'm going to look at two other circles. Let's get two different ones though. There we go. So here, again, think about what the minimum amount of transformations would be to map the green onto the blue. And you can get as specific as possible. Okay, so for this one, we're still going to have to start off with a translation, but this time we only need to move it up. We don't have to move it left or right. And here, well, we don't actually have to use a dilation, right? Because they're already the same size. So our scale factor is going to stay right at 1, which means the green circle is not going to change. So does this fit the definition of similar figures? Yes, we used a translation, which is one of those 4 transformations. We don't have to use a dilation to prove that they're similar, but we're allowed to. These two circles, right, not only are they similar, they're also congruent, right, because we only had to use a rigid motion to map them onto one another. So you'll see that two figures, if they're similar, two figures that are congruent will also be similar. Not all the time, though, will similar figures be congruent. So congruent figures, always similar, and maybe we should write that down, just so we know. So congruent implies that two figures are similar. However, similar does not always imply that two figures are congruent. Sometimes that will be the case, right, when the scale factor is 1, but not every time. Whereas congruent figures, that also means that they are similar. Okay, let's do one more. This is in your notes, so if you guys want to play around with this, you can. Again, just pause the video. What would be the transformations necessary to map the green onto the blue? Well, we're going to move the green to the right. We're going to move it down to map those centers together, and then we are going to enlarge it. Not too much. There we go. Okay, let's go back to our notes. It says, given any two circles, what would the process be for showing that they are similar? Be specific. So just think about it. The process was generally the same for all three sets of circles that we looked at. Think about what we did first, second, third, etc., and write that process down on these lines here. Okay, so the first thing we did, first, map the centers together using a translation. Now, you don't have to be specific because there's an infinite number of translations that are possible, right? But that's the type of transformation we used. We mapped the centers together, or sorry, the type of transformation. We mapped the centers together using a translation. Next, use a dilation to make the circles the same size. So once we map the centers together, then we use the dilation to make sure they're the same size. We could either make the circle larger, make it smaller, or as we looked at in one case, we could just keep the dilation factor at 1 because the circle didn't need to change sizes at all, it just needed to be kept the same. But this is what the process would be. Again, map the centers together, then use a dilation. Let's do some practice. Only 2 practice problems. And you're going to prove that these circles are similar by stating what the transformations would need to be, right? So there's always going to be 2, unless that dilation factor is just 1, but generally there'll be 2. So state the first transformation, be as specific as possible, tell me what type of translation needs to occur, and then tell me what type of dilation needs to occur. And you will need to give the scale factor, right? So you'll need to say translated in this way, and then dilated by a scale factor of blank. And then just make sure you're following the instructions. So it says show that A can be mapped onto B. So you'll be moving A. For number 2, C mapped onto D, so you'll be moving C. So pause the video for a couple of minutes, attempt that, and then come back and see if you did it correctly. Okay, so for the first one, all we need to do is translate 5 units right. And there's a couple different ways you could write it. You could write it in words. You could also write it using symbols. So you're adding 5 to each x value. You're not adding anything to the y values. Your second transformation, dilate by a scale factor of 2. And you may be wondering, well, how do we know exactly what the scale factor should be, right? Do we need to pick points? or is there some other way? And the answer is you can actually compare the radii of the circles. So scale factor. To find that, you can do the radius of the image over radius of the pre-image. So just like we did sides for polygons, right? We did a side of the image over a side of the pre-image. For circles, the dimensions of a circle, you could do circumference, but then you have to calculate something else out. The easiest one is just to do the radius. So the radius of the image over the radius of the pre-image. And of course, the radius of the first circle, 1. Radius of the second circle is 2, so we get 2 over 1. Let's look at the second set of circles. Slightly more complicated translation here. We are going to translate 6 units to the right and 1 unit up. Translate 6 units right and 1 unit up. The other way we could do that, if we are going 6 to the right, we are doing x plus 6, and 1 unit up would be y plus 1. Second transformation, the dilation. Well, again, we're going to compare the radii. So radius of the image over radius of the pre-image. Radius of the image, radius of the image is 3. Radius of the pre-image is 2, so we get 3 halves. So we would say dilate by a scale factor of 3 halves, or 1.5. And we could always check to make sure that it makes sense, right? We're going from a smaller circle to a larger circle, so our scale factor should be greater than 1. Same thing in number 1, right? We're going from a smaller circle to a larger circle, so our scale factor should have been greater than 1. And both of these are. Okay, that's going to wrap up our discussion of how to prove that circles are similar. Hopefully we've seen that regardless of whatever circles we are given, we could always prove them similar using this method, using a series of transformations where the first one is a translation, where we map the centers together, and then we dilate the circle by a certain scale factor. All right, enjoy the rest of your day, and we will look forward to seeing you for our next lesson.